In this lesson, we'll be looking at intercepts and symmetry. An intercept is where the graph crosses or touches an axis. In the example of the graph given here, notice the graph crosses the x-axis in 3 different places. So we have 3 x-intercepts. The graph also crosses the y-axis once. So we have 1 y-intercept. If we wanted to solve algebraically and find those x-intercepts and y-intercepts, we're going to need to make a substitution. To find an x-intercept, we're going to plug in 0 for y and then solve for x. To find a y-intercept, we plug in 0 for x and then solve for y. For example, let's algebraically find the x and y-intercepts for the following graphs. We'll start with the x-intercept, and remember, anytime you're finding an x-intercept, we're going to make y 0. So we're going to set y equal to 0. Y equals x squared plus 5x plus 6. And then we want to solve for x. This is a quadratic, so we'll factor. We need 2 numbers that multiply to 6 and add to 5. That is 2 and 3. Set each of those factors equal to 0. And then solve those equations. X is -2 and x is -3. So the x-intercepts, if we wanted to write those as coordinates, the x value is -2, the y value we set as 0, the other one, x value is -3, and the y value we set as 0. So these are the x-intercepts. To find a y-intercept, we're going to set x equal to 0. So in this case, y is equal to 0 squared plus 5 times 0 plus 6. And we get y equals 6. Or if we wanted to write this as a coordinate, we make the x value 0 and the y-intercept is 6. In the next example, let's find the x-intercept. Again, to find the x-intercept, we simply make y 0. So we're going to substitute a 0 in for y and solve. Solve for x. 2x equals 6, divide by 2, and we get x is equal to 3. So our intercept is 3, 0. To find the y-intercept, we make x 0. 2 times 0 plus 3y equals 6. 3y equals 6, divide by 3, and y is equal to 2. So if we wanted to write that as a coordinate, 0, 2. Next, we'll look at symmetry. There's 3 kinds of symmetry that we're going to be focusing on. The first, symmetry about the y-axis. Consider the graph that we have here, y equals x squared. Notice that if you folded your paper or if you folded the screen along the y-axis, the curves would lie on top of each other. That's symmetry about the y-axis. You can sort of see a mirror image across the y-axis. Notice that the points 2, 4 here and -2, 4 are both present. They're both on the graph. That's indicating that we have symmetry about the y-axis, because no matter what point you have xy, if you also have -xy, then we have symmetry about the y-axis. Another example we could look at, notice that 1, 1 is present, therefore -1, 1 must also be present in order to be symmetric about the y-axis. For symmetry about the x-axis, consider the graph x equals y squared. Note that 4, 2 is on the graph, so the coordinate 4, 2 is on the graph, and also for -2 is on the graph. This can be true for any xy value. So if we look at xy, x negative y must also be there. Another example, if we choose the point 1, 1, notice that 1, negative 1 is also there. For any xy coordinate, x negative y is also there. Also, looking at the graph, imagine if you folded the screen along this x-axis, these curves would lie directly on top of each other. You have symmetry about the x-axis. And then finally, symmetry about the origin. Let's look at this graph and make note of the points 2, 3 here, and also -2, -3. This one's a little bit harder to envision. This one's rotational symmetry. Basically what we're going to do is we're going to rotate the graph 180 degrees or turn it upside down, rotating about the origin. So if you held your finger on this point and spun this graph around 180 degrees, you would get the same picture. That's rotational symmetry, or symmetry about the origin. And notice what we have. We have any xy coordinate, in this case 2, 3, or -2, -3 is also going to be there. So another example, if I gave you 1, 0, then the opposite of x, opposite of y, opposite of 0 is just 0, must also be there. That's symmetry about the origin. Let's look at these examples. Given the point 2, -5 is on the graph and it's symmetric about the y-axis, find at least one other point on the graph. So if we know that 2, -5 is on the graph and we know it has symmetry about the y-axis, if you want, you can sketch it. You don't have to, but 2, -5 is somewhere down here. 2, -5, and we know it's symmetric about the y-axis. That means your other point must be somewhere over here if we're symmetric about the y-axis, and that coordinate would be -2, -5. You're changing the x value. The next example, given the point -3, 1, that should be a comma. -3, 1 is on the graph. Again, we don't have to sketch it, but we can if it helps. -3, 1 is somewhere here. If we know that that point is on the graph, and we also know that it is symmetric about the origin, that means we're going to change the sign of both coordinates. So it's got to be down here. We're going to have +3, -1. If we're algebraically testing for symmetry, to test the y-axis, we're going to replace x with -x and look at the result. For the x-axis, we're going to replace y with -y, look at the result. And to test for symmetry about the origin, we're going to replace x with -x and y with -y and look at the result. Sometimes we may need to multiply both sides by -1. We'll take a look at that when we need it. For example, let's test this first equation for symmetry. We'll start with the x-axis. Remember, to test for symmetry about the x-axis, we replace y with -y. -y is equal to 2x to the 4th plus 3x squared plus 1. Our goal is to compare this to the original. Right now it does not look like the original. Let's try to isolate y by multiplying by -1. So if we multiply by -1 on both sides, it's going to change the signs. You'll get y is equal to negative 2x to the fourth minus 3x squared minus 1. And now compare this to the original. Notice that this is not the same as the original. Those equations are not equivalent. Therefore, we're not symmetric about the x-axis. Next, let's test for symmetry about the y-axis. To test for symmetry about the y-axis, we replace all of the x's with negative x. Y is equal to 2 times negative x to the fourth plus 3 times negative x squared plus 1. And now we need to simplify. Negative x times negative x times negative x times negative x, or negative x to the fourth, is going to become positive. We have 4 negative signs. And then negative x squared, that becomes a positive x squared. So we have 3x squared plus 1. And notice that this is equivalent to what you started with. Those equations are the same. So we know that we have symmetry with respect to the y-axis. I'm going to abbreviate there. Symmetry with respect to the y-axis. Now, if you have symmetry about the y and you don't have symmetry about the x, we really don't need to check for origin, but let's do it just to practice. Let's test for symmetry about the origin. In order to test for symmetry about the origin, we replace both x with negative x and y with negative y. So negative y is equal to 2 times negative x to the fourth plus 3 times negative x squared plus 1. And now we need to go through and simplify this. Negative y is equal to 2x to the fourth plus 3x squared plus 1. Again, we'll multiply both sides by negative 1 to force y to be positive. And we get y equals negative 2x to the fourth minus 3x squared minus 1, which is not what we started with, so we know it's not symmetric about the origin. In the next example, we'll start by testing for symmetry about the x-axis. Again, to do that, we replace y with negative y. And again, in this case, we're going to try to force y to be positive by multiplying both sides by negative 1. When we do that, we can see that these are not equivalent. Your result is not what you started with, so we know it's not symmetric about the x-axis. To test for symmetry about the y-axis, we're going to replace x with negative x. And here we can fairly quickly see that this is not what you started with. So we do not have symmetry about the y-axis. You cannot automatically say it's symmetric about the origin, though. It may have no symmetry. So let's test it. Let's see if it's symmetric about the origin or not. It is possible to have no symmetry. To test for symmetry about the origin, we're going to replace y with negative y and x with negative x. Our goal is to try to force y to be positive here, so let's multiply both sides by negative 1. And notice that this is what you started with. They are equivalent, so we have symmetry with respect to the origin. In our next example, we'll start with the x-axis. Let's test for symmetry. Replace y with negative y. And here we're going to multiply by negative 1. Try to force y to be positive. So on the left we get positive y, and on the right we can distribute that negative sign with the top or the bottom, but not both. Remember that if you multiplied the negative 1 on the top and the bottom, you're technically multiplying by positive 1, which we don't want to do. So distribute that negative sign to the numerator or the bottom, the denominator, but not both. So I'm going to distribute the negative to the top. And now we can see that this is not equivalent to what we started with, so we do not have symmetry about the x-axis. Y-axis. We're going to replace all of the x's with negative x. And simplifying, we get negative x over x squared plus 1, which is not what we started with, so we do not have symmetry about the y-axis. We cannot automatically say it's symmetric about the origin. We have to test it. Again, it is possible that we have no symmetry. So to test symmetry about the origin, replace y with negative y, and we will replace all of the x's with negative x. Negative y equals negative x over x squared plus 1. Again, we want to multiply by negative 1 to get y by itself, get that positive y. So we have y equals, I'm going to distribute the negative sign to the top. We get x over x squared plus 1, which is what we started with. So we have symmetry with respect to the origin. In the next example, we're going to graph the equation x plus y squared equals 4. Let's start by finding the intercepts of the graph. So the x-intercepts, remember, to find an x-intercept, algebraically, we force y to be 0. So let's set y equal to 0 and solve. We get x equals 4. So there's our x-intercept. To find a y-intercept, we make x 0. So we have 0 plus y squared equals 4. Y squared is equal to 4. Take the square root of both sides, and remember, anytime we take the square root of both sides, we need to add that plus or minus. Square root of 4 is 2. So the y-intercepts are 2 and negative 2. Part B asks us to test for symmetry about the x-axis. Again, to test for symmetry about the x-axis, we're going to replace y with negative y. So we have x plus negative y squared equals 4. Let's simplify this. X plus y squared equals 4. That is equivalent to what we started with. So it looks like we have symmetry about the x-axis. So we are symmetric with respect to the x-axis. So I'll make a little mental note to come back to that later. See how that helps us with the graph. Let's go ahead and test the others just to see. Y-axis. Again, to test for symmetry about the y-axis, we're going to replace all of the x's with negative x. So we have negative x plus y squared equals 4. Notice that this is not equivalent to what we started with. There's no simplifying that we can do here. So we do not have symmetry about the y-axis. And then symmetry about the origin, we replace x with negative x and y with negative y. And we want to simplify. Negative x plus y squared equals 4 is not equivalent to what we started with. So we do not have symmetry about the origin. We have symmetry with respect to the x-axis, as we proved earlier. So if we know we're symmetric about the x-axis, we know that we can fold the paper or fold the screen here along the x-axis and have those points line up. So it looks like we're having something like this. And that's our graph.